Dawn creeps slowly through the canopy. Shafts of white gold light filter down through dripping vines, brushing over the buttress roots of a tiba tree. Somewhere in the leaf litter below, a column of ants begins to stir, black, lacquered and purposeful. Paraponera clavata, the bullet ant, moves like a slow wave of intention. Each step of the workers cuts through the silence of the forest floor with a sense of inevitability, as if the jungle itself knows to give them space. For millions of years, this species has held a peculiar crown, not the deadliest, not the most numerous, but the most painful. Every ecosystem has its hierarchy of fear, but here, pain itself is an evolved weapon, and the bullet ant is its artisan. The first shot lingers on a sting, captured in microscopic slow motion. The ant arches its abdomen, stinger unsheathing like a spring-loaded dagger. The strike lands in a fraction of a second, but what follows is a cascade of chemistry that unfolds over hours. The venom, a peptide cocktail centered around ponerotoxin, infiltrates sensory neurons and pries open their gates. Sodium channels lock open, nerve fibers begin to fire uncontrollably, flooding the brain with pure, uninterrupted panic signals. The sensation is not just sharp, it's systemic. A localized sting becomes a full-body riot. Within seconds, pain radiates through the arm in waves that burn, pulse, and then settle into a kind of electric paralysis. Researchers have tried to describe it. Some say it feels like being shot. Others, like walking across burning coals with a nail driven through the heel. Justin Schmidt, who once ranked it atop his famous pain index, called it pure, intense, brilliant pain, like fire walking over broken glass. But even those words fall short, because pain at this level stops being language and becomes experience. It is not an injury signal, it's a takeover. The nervous system, overwhelmed, no longer distinguishes between stimulus and damage. It believes it's dying. For smaller animals, the reaction is instantaneous. Tree frogs struck mid-pounce convulse and tumble from the branches. Mantises, paralyzed by neural confusion, curl their limbs inward before toppling into the leaf litter. Even small mammals have been recorded abandoning kills mid-attack after a single sting. The venom is not optimized for death, it's optimized for deterrence. A predator that survives the encounter will never risk it again. That lesson, etched directly into pain memory, spreads faster through evolution than any scar. Humans, however, bring another layer of complexity. Among the Satare Mawe people of Brazil, the bullet ant holds a sacred role in the passage from childhood to adulthood. The initiation ritual, known worldwide for its intensity, involves weaving live bullet ants into ceremonial gloves made from woven leaves. Each ant is sedated during assembly, then revived once the gloves are donned. Dozens of stingers dig into the participants' hands simultaneously. The candidate must endure the pain for 5 minutes without crying out. The physiological storm that follows is astonishing. The nervous system surges with adrenaline. Pain fibers transmit continuous volleys of electrical impulses that overload the spinal cord's gate control mechanisms. Muscles twitch uncontrollably as acetylcholine floods motor junctions. Some participants collapse into feverish hallucination, the brain trying to overwrite the agony with dreamlike imagery. The arms swell, hands tremble for hours, and lingering neural misfires continue into the next day, hence the local nickname, the 24-hour sting. What makes this ritual more than endurance theater is its evolutionary poetry. The Satere Mawe understand pain not as punishment, but as transformation, a rewiring of fear. By surviving, the forest's ultimate warning system initiates earn symbolic harmony with it. The ant teaches resilience by overwhelming it. Modern neuroscience adds another layer. Extreme pain triggers endorphin storms that can reset stress tolerance, potentially altering the brain's threat response calibration. In short, the ritual may genuinely change how the nervous system processes suffering. The camera pans back to the forest floor. A single bullet ant climbs a decaying branch, antennae flicking. Its mandibles test a patch of fungus, while its abdomen hums slightly, ready to strike at any disturbance. Each ant lives for months, but their colonies endure for decades. Underground, workers tend larvae, feed queens, and patrol tunnel corridors that can reach several meters deep. Unlike army ants or leafcutters, bullet ants don't wage wars or harvest fungus. Their empire is built on deterrence. They defend territory with singular ferocity, but rarely expand it. Evolution has sculpted them into guardians rather than conquerors. Their sting, paradoxically, is not heavily laced with toxins designed to kill. The actual dose of Ponera toxin is small, almost minimal by venom standards. But what it lacks in volume, it compensates for in targeting. The compound is exquisitely tuned to exploit mammalian and vertebrate nerve receptors. Instead of destroying tissue or paralyzing prey, it hijacks the language of the nervous system itself, sending false signals of catastrophic injury. It's pain as deception, an illusion so convincing that evolution itself treats it as truth. Pain, in this sense, becomes adaptive currency. In the rainforest, where predation pressure is constant, chemical energy is precious. To waste venom on death is costly. To weaponize pain is efficient. A sting that incapacitates a frog for an hour may save the colony's brood with a single molecule per strike. Over millions of years, natural selection fine-tuned this equation until the bullet ant emerged as the gold standard of biological deterrence: maximum pain, minimum venom. The rainforest responds accordingly. Birds learn to recognize the glossy black sheen of Paraponera workers and give them wide berth. Snakes flick tongues over chemical trails and divert course. Even primates, normally fearless omnivores, pause when they detect the ant's alarm pheromone, an acrid vapor of formic and pyrazine compounds that signals danger in invisible waves. In a place where everything eats and is eaten, the bullet ant exists as a rare constant, a boundary species that enforces respect without needing to kill. As afternoon rain begins to fall, droplets strike the canopy with a soft hiss. The ants retreat to their nest entrances, guarding them like sentinels. The camera follows one worker pausing under a leaf edge, mandibles poised. Its stinger flexes briefly, catching a bead of water, magnifying the curve like a lens. Through that droplet, the forest refracts, green, gold, and endless. This small creature, weighing less than a paperclip, commands the attention of animals 1,000 times its size. Pain here is not an accident. It's communication. Every nerve it hijacks sends a clear message across species lines. Remember me. The predator remembers. The tribesman remembers. Even the scientist, days later, tracing the tingling in his fingertips, remembers. In an ecosystem built on speed and stealth, the bullet ant survives by invoking the one thing nothing forgets: the pure, inescapable lesson of suffering, and that, in the end, is its genius. Evolution rewarded not brute strength or venom potency, but psychological supremacy. The bullet ant doesn't need to win fights, it simply ensures no one wants to start one. In the Amazon, where every shadow hides a hunter, it stands as proof that survival sometimes favors not the quickest or the strongest, but the creature that turns pain itself into armor. The camera lingers on the colony entrance one last time as twilight descends. The hum of insects rises, frogs begin their nightly chorus, and deep beneath the roots, the ants resume their slow, deliberate movement. The forest breathes around them, alive, electric, and aware that somewhere below the leaves, the masters of pain still walk. The rainforest never really sleeps, it just rearranges its shadows. By the time the last cicada has folded its wings and the air thickens with night humidity, the forest floor comes alive with a quieter, more deliberate kind of movement. Between the rotting leaves and fruit husks, a faint vibration ripples across the litter. It is not wind nor the shuffle of a rodent. It's something that feels, listens, waits. Then, with the speed of a reflex, the leaf litter explodes. 8 legs strike outward in a synchronized burst, and before the frog even finishes its jump, it is already paralyzed mid-air. The hunter is the Brazilian wandering spider, Phoneutria fera, Phoneutria nigriventa, and their kin, creatures that hunt not with webs or traps, but with a biological weapons. How severe it can turn a victim's own bloodstream against itself. The camera follows the spider's emergence. Each limb is bristled and powerful, its movements precise rather than frantic. These spiders are not the delicate silk engineers of the canopy. They are terrestrial gladiators, built for ambush and speed. Their world is the detritus, the shifting mosaic of fallen leaves, fungus blooms, and beetle carapaces where scent and vibration carry more meaning than sight. Under infrared, the scene glows faintly as the spider's sensitive leg hairs pick up microcurrents of air, every tremor interpreted as motion data. A cricket lands. For 2 full seconds the spider does not move. Then it lunges forward with a velocity that borders on instantaneous. The strike isn't a reckless attack, it's a calculated neural circuit. Detect, orient, leap, bite. The fangs penetrate with surgical precision, delivering a drop of clear venom that changes everything inside the prey. From the outside, the effect is swift and almost silent. The cricket stiffens, legs jerking in chaotic spasms before collapsing into stillness. But inside, the chemistry is catastrophic. The venom of Phoneutria doesn't just kill, it reprograms. It floods the victim's body with a neurotoxic peptide cocktail that interferes with calcium and sodium ion channels in nerve endings. Communication between brain and muscle fractures. Signals meant to trigger movement begin to overlap and short-circuit. Muscles fire uncontrollably, consuming oxygen faster than blood can deliver it. Blood vessels constrict violently, then fail to dilate, sending blood pressure into free fall. The result is a rapid collapse of systemic control, panic, paralysis, then silence. In rodents tested under controlled conditions, the timeline can be measured in seconds. Within 10, respiration falters. Within 30, convulsions stop. For larger vertebrates, lizards, birds, or unlucky humans, the process takes longer but feels far worse. Victims report burning at the bite site, followed by intense muscle cramps that roll through the body like tides. The nervous system floods itself with stress hormones, heart rate spikes, and then, suddenly, drops. Vision narrows, breath shortens, and the body enters a strange, paradoxical state, conscious, yet powerless. The spider has weaponized the architecture of the victim's own biology. The body, in effect, becomes its own assassin. These spiders' encounters with humans are rare, but not mythical. In parts of Brazil, they are a nightly reality. They wander, hence their name, through banana plantations into storage crates, sometimes into homes. Most bites occur when a person slips on a shoe left outside or pulls back the blanket at dawn. The resulting panic is twofold: the fear of the bite itself and the venom's immediate, unmistakable message that something inside is catastrophically wrong. Victims sweat, shake, and experience crushing chest pain. Hospital records describe arterial blood pressures dropping to levels barely compatible with consciousness. Though fatalities are uncommon with modern treatment, the experience is unforgettable, an evolutionary sermon on the fragility of the human nervous system. In the laboratory, the venom has become a paradoxical object of fascination. Within its complex mixture of peptides lies one component, TX2/6, that interferes not just with neurotransmission, but also with vascular smooth muscle function. It dilates certain blood vessels while collapsing others, creating a biochemical tug-of-war between circulation and collapse. Ironically, this compound has drawn attention from medical researchers for its potential use in cardiovascular therapy and even erectile dysfunction drugs, a twist of evolutionary irony in which a toxin designed to disable life might one day help preserve it. But in the wild, there is no therapeutic dosage, only shock, pain, and the razor-edge efficiency of natural selection. Unlike web builders, the wandering spider has no safety net. It cannot rely on trap geometry or vibration cues transmitted through silk. Every meal must be hunted down, engaged directly, subdued, and eaten before competitors arrive. This lifestyle shapes its entire physiology. The body is larger and more muscular than most ground spiders of similar mass. Its vision, though limited in range, excels in low light, tuned to detect motion even in moonless darkness. Yet its most potent adaptation lies in its behavior, restless motion. While most spiders anchor themselves to one place, Phonutria moves ceaselessly across the forest floor, patrolling territories as large as 20 meters in a single night. This constant wandering reduces competition with web builders and maximizes encounters with prey, but it also exposes the spider to predators. And so, venom becomes both sword and shield. Field observations show that when threatened by birds or small mammals, the spider rears up, front legs extended, fangs bared, a display as theatrical as it is rational. The warning posture is designed to broadcast confidence. Predators pause, and for good reason. The bright reddish chelicerae flash in dim light. The spider vibrates slightly, hissing through rapid leg movements that brush the substrate. It's not just a bluff. If the warning is ignored, the strike follows, and even a large predator like a tamarin or small opossum may stumble away in spasms. Over evolutionary time, such lessons spread. Fear becomes part of the ecosystem's shared vocabulary. To understand how a wandering spider survives, one must see it not as a mindless aggressor, but as a master of chemical economics. Webs require protein silk and fixed territory. Venom requires energy-rich peptides and sophisticated synthesis pathways. For Phonutria, Mobility pays for chemistry. By hunting freely, it encounters higher prey diversity. Crickets, frogs, small lizards, each demanding a different physiological lock-and-key response. Natural selection refines venom complexity accordingly. The result is a formula capable of overwhelming almost any vertebrate nervous system within seconds. That universal potency is no accident. It's a byproduct of flexibility, the price of not building webs in a forest where almost everything else does. Field biologists studying these spiders at night often describe the tension of their work in paradoxical terms. Exquisite terror. Every rustle could be a leaf falling, or an eight-legged predator repositioning. To film Phonutria in motion requires precision lighting and absolute stillness, because vibrations from human footsteps alone can trigger the spider's defensive stance. Yet when the camera captures it, the footage is breathtaking. You see an animal that moves like thought itself, direct, immediate, unhesitating. Its attacks are guided not by rage, but by design, honed through millions of years of perfecting chemical control over chaos. The ecological logic behind such intensity is simple: deterrence through dominance. A web is a structure of patience. Phonutria is an organism of intimidation. The venom doesn't just feed it, it protects it. By making every encounter potentially lethal, the spider reduces its need to fight at all. Few predators risk it twice. Even monkeys, typically curious and bold, learn avoidance after a single close call. On the forest floor, this reputation matters. The wandering spider becomes a moving exclusion zone, a small patch of jungle governed by fear chemistry. As dawn returns and humidity lifts from the ground, the spider retreats into darkness, a hollow in bark, a discarded nutshell, a space just large enough for its coiled frame. Around it, the forest resets for daylight life. Leafcutters march, frogs chorus, and birds resume their frantic calling. The forest forgets quickly, but inside the tissues of every creature that has felt the spider's bite, the memory persists. Pain, paralysis, and that unforgettable racing heartbeat are more than warning signs. They're biological messages encoded in peptide language. Do not touch again. Evolution often hides elegance beneath brutality, and the Brazilian wandering spider is one of its clearest examples. It doesn't weave beauty into silk or build architecture among branches. It walks unarmed except for chemistry, yet wields control over the very systems that make life possible. Its weaponry does not aim outward, it turns the enemy inward, transforming blood and nerve into chaos until resistance collapses. That efficiency, that precision, explains its enduring success. In a world where most predators rely on force, Phonutria uses panic as a tool. It infects, overwhelms, and ends conflict before it truly begins. Pain becomes performance. Fear becomes survival strategy. The rainforest teaches this lesson repeatedly, that life thrives not by balance alone, but by learning to manipulate imbalance. And on the forest floor of South America, where every shadow hides a hunter, few manipulations are as absolute or as unforgettable as the panic carried in a single drop of venom from the wandering spider. The river at night looks peaceful, still, almost glassy, but beneath its black water surface lies a constant voltage. Each submerged branch and root shadow could be hiding the Amazon's strangest apex hunter, one that kills without claw or fang. The electric eel, Electrophorus voltae, and its kin, rule by invisible force. Their domain isn't defined by territory or speed, but by control, of current, of distance, of pain. To see one hunt is to witness electricity itself sculpted into a weapon, and to understand that the river's silence is charged with potential violence. As the camera sinks below the meniscus, the world turns amber and green. Shafts of weak light flicker through suspended silt. A suspended leaf drifts past. Then, from the gloom, a thick, snake-like form emerges, dark olive, rippling with slow, confident movement. Around it, smaller fish scatter in erratic bursts, sensing the faint, rhythmic pulses emitted from the eel's body. These low-voltage signals, like radar pings, map the world in electromagnetic contours. Every root, pebble, or swimming creature sends back a signature, allowing the eel to see in total darkness. It glides like a living voltmeter, its entire body a sensor array. When it chooses to strike, that same body transforms from receiver to transmitter. Beneath the skin, hundreds of thousands of specialized cells called electrocytes align in stacks, each capable of generating a tiny charge. On their own, they are unremarkable, cells not so different from those in a human heart. But wired in series like microscopic batteries, they become a living power grid. When the eel decides to fire, nerve impulses sweep down its body, opening ion channels across each cell in perfect synchrony. In less than a millisecond, the stacks discharge together, producing up to 860 volts, enough to stun a horse. The effect underwater is immediate and spectacular. Fish within a meter convulse as their motor neurons overload, forcing every muscle to contract at once. The water seems to shiver with invisible energy. The eel moves in, eyes dull but deliberate, sending a second burst, shorter, sharper, like a taser's aftershock, to lock the prey in total paralysis. The double pulse is key. The first blast reveals hidden targets by making them twitch. The second immobilizes them. It's not just brute electricity, it's a form of sensory manipulation. The eel reads movement through its own field, forces the prey to betray its position, then shuts it down. To the eel, each fish is a light switch. With every discharge, it can flick that switch off at will. Once the prey stiffens, the eel glides forward, mouth opening in a slow, mechanical arc. The fish disappears whole. There is no chewing, no tearing, no blood. Only a faint tremor from the eel's body as it swallows, and then calm again, voltage dormant, but ready. Laboratory tests have confirmed what field biologists long suspected. The electric eel's shock isn't just powerful, it's patterned. When scientists placed electrodes near hunting eels, they found bursts delivered in rhythms, not random intervals. Short volleys during pursuit, longer sustained shocks for defense. It's a living symphony of current, fine-tuned through evolution to handle different biological problems. High-voltage discharges are costly. They deplete stored ions and require time to recharge. But in a system where milliseconds decide survival, efficiency matters. The eel's brain regulates output the way a conductor guides tempo, balancing detection, offense, and intimidation. The intimidation aspect is as fascinating as the kill itself. River mammals, capybara, dogs, even humans, learn quickly to respect the electric eel's strike zone. When threatened, the eel doesn't flee. It rises. With serpentine force, it thrusts its body upward, pressing its chin against the intruder and delivering its full voltage through direct contact. This jumping defense, as researchers call it, transforms the eel into a biological defibrillator. Current flows through the attacker's body to the water surface, where resistance is highest, maximizing the jolt. A human standing in shallow water can feel their muscles lock, breath vanish, and vision narrow to white static. It is not lethal under most conditions, but it is unforgettable. The body interprets it as being struck again and again, nerves flooding the brain with alarm signals faster than consciousness can process them. To an animal, that lesson is final. Few ever test it twice. Caimans abandon ambushes mid-lunge, monkeys avoid river shallows at night, and even large predatory fish divert when they detect an eel's electric field. In a habitat where almost every creature has evolved armor, camouflage, or venom, Electrophorus has achieved dominance through remote deterrence. It rules by pain, delivered cleanly through physics, never needing to pierce the skin. There is an austere elegance in this method. Electricity predates muscle and bone. It was the language of the first nervous systems. The eel merely reclaims it. Its weaponry is an exaggeration of the very principle that allows animals to move at all. Every heartbeat, every blink of an eye is the firing of charged membranes. The eel takes that universal mechanism and amplifies it to military scale. In doing so, it bypasses the entire evolutionary arms race of claws, fangs, and toxins. It doesn't puncture or poison. It hijacks. It reaches inside its victim's biology and turns the nervous system against itself. During the dry season, when shrinking pools trap fish in crowded pockets, electric eels switch from solitary to cooperative hunters, an almost unheard-of behavior in predatory fish. Groups of up to a dozen individuals herd schools of small caracons into tight balls near the surface. Then, in coordinated bursts, they attack, releasing synchronized volleys that send fish scattering in seizures. The spectacle, captured on drone and submersible footage, reveals something profound. Intelligence in electrical timing, a kind of choreography performed through shock waves. Every pulse communicates dominance, forcing the prey into a corner until exhaustion sets in. For humans, encounters with electric eels are reminders that pain doesn't always draw blood. Historical accounts from explorers and river travelers are filled with stories of mules collapsing midstream or fishermen losing consciousness after an unexpected strike. Even now, rural locals treat the eel with cautious reverence, calling it paralyze, the one that makes you fall, and fall they do. Victims often experience full-body muscle lock, sometimes leading to drowning if the shock occurs in deep water. Despite centuries of proximity, the eel remains both familiar and alien, a symbol of power that is everywhere and nowhere at once. Physiologically, its endurance borders on miraculous. To generate such immense voltage repeatedly, the eel must maintain enormous ionic gradients across its electrocytes, something it does by constantly consuming oxygen from the air. Unlike most fish, it is an obligate air breather, surfacing every 10 minutes to gulp a bubble. Each breath fuels the ionic pumps that reset its internal batteries. In oxygen-poor backwaters where other species suffocate, the eel thrives. The murkier and stiller the channel, the more dangerous it becomes, because stillness amplifies the reach of its electrical field. But perhaps the most astonishing thing about the electric eel is not its power, but its restraint. Most of the time, its discharges are exploratory, low-voltage communications, a language of tiny pulses that map the world and signal intent. When it escalates to full power, it does so with the precision of a sniper. Even in experiments where multiple prey items were offered, the eel targeted one at a time, never wasting energy on unnecessary shocks. Its electricity is both sensory organ and sword, fused into one seamless biological system. In ecological terms, this specialization fills a unique niche. In rivers crowded with predators, piranhas with shearing jaws, caimans with bone-crushing bites, anacondas with suffocating coils, the electric eel occupies the role of enforcer. It doesn't chase, it declares. Its message travels faster than sight, faster than sound. Do not approach. By weaponizing nerve conduction itself, it ensures that even those who survive the encounter carry the memory in their muscles for life. As the sequence closes, the camera pans along the surface of the river. A faint drizzle ripples the water, scattering reflections of the canopy above. Beneath, an electric eel lies coiled in the silt, motionless except for the slow rise and fall of its gill covers. Small fish orbit nervously at a distance, testing boundaries they cannot see. Then, for a moment, a flash, so brief it might be imagined, ripples through the darkness. The river twitches, and all motion stops. No blood, no teeth, no sound, just voltage, the purest expression of predation, invisible force, immediate consequence. In the Amazon's endless theater of survival, the electric eel rewrites the rules by turning life's own spark into a weapon. Pain becomes a broadcast, a deterrent, a memory that spreads through generations of river life. And long after the current fades, the silence that follows hums faintly with respect for the hunter that rules by touchless control, the architect of pain without teeth. In the dim underworld of the Amazon rainforest, where light barely filters through the layered canopy, the forest floor exists in a half-shadowed eternity. It is a place of patience and silence, where stillness itself becomes a weapon. Between fallen palm fronds and rotting fig leaves, a shape lies coiled and unassuming. Its body mirrors the litter around it, scales etched in the same mottled ochres and browns as decomposing vegetation. Only the faint patterning, a subtle lattice of diamonds fading into the soil, betrays the presence of one of the jungle's most formidable predators. This is the bushmaster, Lachesis muta, the largest pit viper in the Americas and perhaps the most ghost-like of them all. The bushmaster does not chase, it waits. For hours, sometimes days, it remains unmoving along narrow forest corridors where agoutis, pacas and peccaries thread their habitual paths. The patience is absolute, muscles locked, respiration barely perceptible. The only part of its body that seems alive is the tongue, a dark, flickering ribbon tasting the air for heat and chemistry. When prey approaches, the snake's body tenses in a slow, invisible coil. Infrared sensing pits along the face read the target's body heat, sketching a thermal silhouette in perfect darkness. Then, without sound or warning, the strike erupts. A whip crack of movement, fangs driven deep, a flash of muscle torque, and the forest returns instantly to silence. Many victims never even see what hit them. The bushmaster's strike is not just a mechanical act, it is a chemical declaration. Its fangs, hollow conduits the length of a human finger, inject a venom that operates like a layered symphony of destruction. The first notes are pain, immediate, burning, almost electric. Victims thrash and claw at the bite site as tissue begins to swell within minutes. But beneath the surface, far more insidious processes are unfolding. The venom's enzymes, chiefly metalloproteinases and serine proteases, dismantle blood vessel walls, releasing plasma and red cells into surrounding tissue. The result is both hemorrhage and clotting, a paradoxical chaos where blood thickens in some vessels and seeps uncontrollably from others. Muscles begin to die from within, and as they decompose, the body releases molecules that trigger systemic inflammation. Over hours, the victim's own immune system amplifies the injury, turning pain into a spreading, self-perpetuating storm. For small mammals, a rodent or a young bird, the effect is swift. Shock sets in within minutes. The heart succumbs to hemorrhagic collapse before the animal travels far. But for larger prey, including primates or humans, the process stretches across hours or even days. The swelling can engulf entire limbs, cutting off circulation as if the flesh itself were turning to stone. Victims report waves of burning pain that crest and recede, each sharper than the last. Vision may blur, skin darken around the wound, and breath grow shallow under the strain of collapsing blood pressure. It is not a fast death, nor a merciful one. Yet, to the bushmaster, it is strategy, not cruelty. The logic of this slow burn lies in the forest itself. In dense vegetation, where sight lines are short and movement muffled, tracking prey after a clean strike would be nearly impossible. A lethal venom that kills instantly would leave the body far away, lost to scavengers or hidden beneath roots. The bushmaster's chemistry solves this elegantly. It weakens, incapacitates, and ensures the victim cannot travel far. The wounded animal's internal bleeding leaves a scent trail of hemoglobin and decaying proteins that lingers in the humid air. An invisible path the snake can follow at its leisure. Its heat-sensitive pits pick up the residual warmth of the dying body, even hours later. In this world of decay and darkness, a slow death is easier to find. Ecologically, this makes the bushmaster less an assassin and more a collector. Its method relies on attrition rather than pursuit. It invests heavily in venom volume, among the largest of any snake species, precisely because every drop must compensate for the delay between strike and meal. Once the prey is found, the snake's role reverses. It becomes almost gentle. The feeding process is slow and deliberate, the jaws expanding impossibly wide to accommodate the body of a rodent or small marsupial. For hours, the predator works silently, muscles rippling in waves as it draws its meal inward. Then, replete, it withdraws once more into stillness, sometimes remaining motionless for days to digest. Despite its power, the bushmaster remains elusive. Even seasoned herpetologists spend years without glimpsing one in the wild. It is a snake built for secrecy, cryptic coloration, nocturnal habits, and a preference for deep primary forest where human presence is scarce. Local people speak of it with a mixture of awe and superstition, calling it Surukuku, the silent one. The name fits. Unlike rattlesnakes, its New World cousins, the bushmaster gives no audible warning before it strikes. Its rattle is vestigial, tiny scales at the tail tip that make no sound. Its defense is invisibility. When encounters with humans do occur, they are often accidental and tragic. Farmers or loggers stepping through dense undergrowth may brush against one coiled beneath leaves, provoking an immediate defensive bite. The outcome depends on distance to medical care. Antivenoms exist, but must be administered quickly. Even survivors describe pain that lingers for months and scars that mark tissue loss. Laboratory analysis shows that the venom's proteins continue to disrupt cellular repair long after neutralization, a reminder that evolution engineered this mixture not for instant results, but for endurance. From a biological standpoint, the bushmaster's venom tells a story about energy and efficiency. Predators that rely on speed, like jaguars or harpy eagles, must burn enormous calories to sustain their hunts. The bushmaster spends almost none. Its metabolism is slow, its strikes rare, its meals large. Venom becomes the investment fund that guarantees returns on minimal effort. Each molecule of toxin represents energy the snake will recover later in the form of flesh. Pain, swelling, and bleeding are side effects only from the victim's perspective. From the snakes, they are tracking devices, biological breadcrumbs that mark a path through chaos. In ecological balance, such predators play an unglamorous but vital role. By targeting weak or careless individuals, they regulate small mammal populations that might otherwise overgraze the forest floor or spread disease. They also serve as prey themselves for larger carnivores, particularly ocelots and king vultures, that occasionally find and consume them. Even in death, the bushmaster's presence shapes nutrient cycles. Its decomposing body enriches the very soil that conceals its kin. Everything in this forest is both predator and prey, both participant and process. There's an irony in how rarely these snakes strike compared to their reputation. Field telemetry studies have shown that adult bushmasters may feed only a handful of times per year. Each strike is a calculated gamble, refined by instinct and energy conservation. Their venom glands refill slowly, and producing new toxin costs valuable protein and minerals. To bite is to invest. This makes the species surprisingly tolerant of proximity. Many potential encounters with humans end not in attack, but in withdrawal. It is patience, not aggression, that defines them. To watch one up close, coiled, breathing softly under dappled light, is to understand evolution's long game. Every part of its anatomy exists to disappear. The keeled scales break up reflections, the eyes sit high to monitor movement without exposure, and even the heat pits blend seamlessly into the facial patterning. When the wind moves the leaves, the snake moves with them, just enough to remain indistinguishable from the ground. It is not hiding, it is the forest floor. And yet, inside that motionless body lies a system calibrated for devastation. The venom doesn't just kill, it instructs. It teaches every animal that survives it the meaning of suffering, imprinting avoidance into the ecosystem's behavioral memory. Even predators that could theoretically overpower the bushmaster, such as jaguars or tigers, learn to read its smell and posture. Fear becomes another layer of its camouflage. As dusk falls, a camera pans low across the forest floor. Fireflies drift like embers in the gloom. Somewhere ahead, the soft scrape of claws, an agouti foraging among fallen fruit. The snake's tongue flicks once, twice. The forest holds its breath. When the strike comes, it is almost anticlimactic, a flicker of movement and silence again. The agouti bolts, then slows, then falters. Minutes later, its heartbeat stumbles into stillness. The bushmaster does not follow immediately. It waits, sensing, letting time do what venom has begun. Pain travels faster than footsteps. and in the humid stillness of the Amazon night, both predator and prey are bound by it. Hours later, guided by scent and heat, the snake will reclaim what patience and chemistry have earned. In the end, the bushmaster's mastery lies not in its size or its strength, but in its control over inevitability. Its weapon is not the quick certainty of death, but the long, unfolding inevitability of it. A slow bleed, a deep pain, a memory written into the muscles of the forest. On this floor of endless decay, it stands as monarch, not because it kills quickly, but because nothing escapes the reach of its patience. Morning light filters through the canopy like liquid gold, catching on the broad green leaves that seem to pulse with life. The camera drifts in close, past dew beading along a vine, past the microcosm of ants ferrying pollen, until it settles on a single leaf, trembling ever so slightly. At first, the movement looks like a breeze. Then the focus sharpens, and what seemed to be a patch of moss or fine velvet reveals itself to be a living organism, soft-bodied, leaf-colored, and almost endearing. A caterpillar. But in the Amazon, softness is often a lie. Those delicate hairs are not decoration. They are needles. Each strand hides a syringe. This is one of the rainforest's strangest paradoxes. Creatures that appear harmless, commanding the same level of respect as its apex predators. The venomous caterpillars of South America, especially the infamous Lonomia genus, sometimes called assassin caterpillars, have rewritten the rules of defense. They don't chase, ambush, or even move much at all. Their entire survival strategy rests on the principle that pain can be broadcast through touch. Evolution has turned passivity into power. In slow motion, we watch as a monkey, a young capuchin, reaches for a branch draped in the shade of a cecropia tree. Its hand closes around a cluster of leaves, and instantly the animal jerks back, shrieking, shaking its arm violently. The caterpillar tumbles to the forest floor, unharmed. The monkey's hand, however, reddens as if scorched. Within seconds, the pain spreads, deep and searing, radiating through the limb. The cause is invisible to the naked eye. Hundreds of microscopic spines embedded in the skin, each tipped with venom. Under magnification, the hairs of these larvae resemble glass harpoons. When pressed, they snap at the base and inject their contents, a mix of anticoagulants, proteolytic enzymes, and potent neurotoxins, directly into the skin. The chemistry varies between species. Some produce localized agony and swelling. Others, like Lonomia obliqua, the species responsible for several human fatalities, unleash systemic chaos. Their venom disrupts blood clotting by activating both coagulation and fibrinolysis at once, effectively making the blood clot in some vessels while pouring freely from others. Victims can develop internal bleeding, kidney failure, or, in severe cases, fatal hemorrhage. For a creature barely the length of a human finger, the scale of such power borders on absurdity. Yet, in evolutionary terms, it makes perfect sense. Birds, monkeys, and small mammals routinely comb foliage for protein-rich larvae. A single defensive innovation capable of turning one encounter into lifelong avoidance pays off instantly. Pain becomes a teacher. The rainforest runs on such lessons. One wrong touch, one scream of pain, and an entire troop of foragers alters its behavior. Predators evolve memory as a survival mechanism, not for themselves, but for their prey. The forest canopy is full of such silent negotiations. Birds scan leaves not just for color, but for texture and outline. Experiments with decoy models show that many species of tanagers and flycatchers avoid caterpillars that display certain fur-like silhouettes, regardless of color pattern, an instinct learned the hard way. Over generations, these defensive postures have sculpted visual culture in the forest. The most dangerous larvae no longer need to be seen. They simply need to resemble the memory of pain. For humans, encounters are often accidents of curiosity or carelessness. Field biologists collecting foliage samples or locals reaching for low-hanging fruit sometimes brush against these camouflaged insects. The reaction can be dramatic, burning pain within seconds, swelling and blistering soon after. In severe lonomia cases, victims report muscle cramps, dizziness, and spontaneous bruising as the venom begins dismantling vascular control. Some have required transfusions to survive. Hospitals in parts of Brazil and Colombia now stock specialized anti-venom, an extraordinary measure for an animal that, strictly speaking, doesn't attack. To understand how such toxicity evolved, one must look at the caterpillar's place in the food web. These larvae are transitionary creatures, temporary embodiments of vulnerability. They live exposed on leaves, unable to fly, unable to flee, devoured by nearly every predator that can reach them. The rainforest is an arms race, and in that race, chemistry offers the shortest route to equality. Each species of venomous caterpillar represents a different evolutionary experiment in chemical deterrence. Some load their spines with histamine-like compounds that provoke instant inflammation. Others secrete proteases that digest skin on contact, amplifying the sensation of burning. Lonomia, by contrast, chose complexity, venom that attacks the body's clotting system itself, ensuring that the price of touching it extends far beyond the surface. From an ecological standpoint, this strategy transcends individual defense. It establishes a behavioral boundary across species. When one monkey screams, others learn. When one bird loses its appetite after a sting, its offspring inherit a bias against similar shapes. The forest becomes an information network where pain travels faster than any signal. Over time, entire communities of predators adjust their foraging habits, sculpting the evolutionary trajectory of both hunter and prey. The caterpillar, in its stillness, influences the architecture of the canopy. In macro view, the forest's daytime serenity hides a battlefield of textures. Leaves host an array of caterpillar species, some lined with bright warning colors, others cryptic and perfectly disguised. A single branch may carry 3 or 4 different evolutionary answers to the same question: how to survive being eaten. Among them, the venomous species occupy an interesting middle ground. They often forego vivid coloration, blending into their host plants. Why advertise danger when discovery itself is already painful? This cryptic approach works best in biodiverse systems like the Amazon, where sensory overload keeps predators guessing. The forest's complexity becomes part of the caterpillar's camouflage. The camera now pulls tight on a lonomia resting across a fern stem. Its spines glisten with morning dew, each droplet refracting the green canopy above. The larva moves slowly, rhythmically, its body flexing as it consumes a patch of leaf. It has no idea that its chemistry has reshaped local animal behavior, no concept of deterrence or pedagogy. Yet its existence embodies the rainforest's central rule. Survival is not about aggression, but communication. Pain, here, is language. Elsewhere, a bird lands on a nearby branch. It studies the leaf surface, cocks its head, and then hops away, choosing another perch. A monkey, watching from the next tree, follows its lead. The bush below remains untouched. The caterpillar continues feeding in perfect safety. There is a subtle irony in all this. The venomous caterpillar, destined to become a harmless moth, invests its greatest biological power in a stage of life that will soon be shed and forgotten. As adults, these same species are delicate, non-venomous pollinators that live only days or weeks, often without mouths. Their legacy of pain serves no purpose beyond protecting the juvenile self that will one day metamorphose into gentleness. It is a form of evolutionary front-loading, suffering as insurance for transformation. In ecological terms, the caterpillar's venom plays a stabilizing role. By discouraging overpredation, it ensures that certain plant species retain their natural pruning agents. The larvae feed selectively, trimming leaves and promoting new growth. Too many losses to predators and the balance would collapse. Leaves would overaccumulate, light levels would drop, microclimates would shift. The pain economy of the canopy is, paradoxically, an engine of equilibrium. For the animals of the Amazon, pain is not just punishment, it is feedback. It teaches boundaries, what to touch, what to eat, what to avoid. The venomous caterpillar contributes to this silent education system more effectively than most predators could ever hope to. It costs nothing in pursuit, spills no blood, and yet changes the behavior of entire species. Each sting becomes a broadcast message written directly into nerve and memory. As afternoon rain begins to fall, the camera pulls back from the leaf. Droplets cascade over the forest, pattering like static across millions of hidden surfaces. Somewhere above, monkeys chatter restlessly, but stay clear of certain branches. Birds preen on safe perches, having learned their shapes by heart. And on one wet green leaf, a caterpillar continues its slow meal, glistening like an ornament of the storm. It doesn't hunt. It doesn't flee. It simply waits, defended by the memory of every creature that has ever touched one of its kind. In the vast equation of the Amazon, where pain defines survival and learning defines longevity, this small, soft insect wields an influence out of all proportion to its size. Pain may fade, but its lesson endures, and in the canopy's unspoken calculus, that lesson is power. The Amazon River breathes like a living lung. At dawn, its surface lies still, a pale mirror reflecting clouds that stretch in muted ribbons of pink and silver. Beneath that calm, the river bottom stirs, a slow undulation of sand, the faint sigh of sediment settling. Here, in the shallows where roots braid into silt and light flickers like diluted gold, lies one of the jungle's most deceptive inhabitants. It has no fangs, no claws, no hunger for confrontation. Yet it may inflict the most unforgettable pain in all of South America. The freshwater stingray, buried and invisible, waits not to strike, but to survive. Its camouflage is perfect. A film of fine sand dusts its disc-shaped body, leaving only a faint outline visible if the light catches just right. Two small eyes and a spiraled pair of breathing holes, spiracles, just behind them. Through these, the ray draws water in, pushing it across its gills while keeping its mouth buried. To the untrained eye, it is nothing but riverbed. Only when something disturbs the stillness, a fish, a probing heron beak, or the footstep of a mammal, does the illusion dissolve in an instant. A flash of motion, a plume of mud, and pain erupts from nowhere. The stingray's weapon sits at the base of its tail, a spine, or sometimes two, formed of hard dentine. The structure resembles a serrated dagger, each barb angled backward like a sawtooth. Along its edges, tiny grooves cradle venom glands sheathed in a delicate mucous membrane. When the ray lashes upward, the tail acts like a spring-loaded whip, driving the spine deep into flesh. The serrations tear muscle on entry and anchor themselves so that any attempt to pull away only worsens the wound. The membrane ruptures, flooding the puncture with venom, a biochemical storm of serotonin, phosphodiesterase, and 5 nucleotidase that triggers immediate nerve firing and violent inflammation. Victims describe it as electric and primal. The pain radiates outward in waves, overwhelming logic or thought. Within minutes, the limb swells grotesquely, nausea rises, the body trembles as if gripped by fever. For some, shock sets in, heart rate collapsing under the sheer neurological overload. Even with treatment, hours of throbbing agony follow. Weeks later, the tissue around the wound may still blacken, dying slowly as toxins and bacterial infections battle the body's defenses. To those who have lived through it, the sting is not just pain, it is memory encoded in nerves. For the stingray, though, this brutality is insurance. Life on the bottom of a tropical river is a game of constant vulnerability. The sandy substrate that conceals the ray also hosts armies of scavengers and opportunists. Piranhas sweep through in dense schools, their flashing jaws quick to test anything that moves. Caimans patrol the margins, noses barely above the surface. Even jaguars, those terrestrial kings, descend to the shallows to fish. Against such a cast of predators, speed and teeth mean little for a flat-bodied creature that spends most of its life half-buried. The stingray's spine is not an attack. It is deterrence distilled into anatomy. Underwater footage reveals the subtle intelligence of this defense. A caiman's snout probes the sand where a ray lies hidden. The stingray does not move at first. Stillness is safety. Only when pressure increases, when danger crosses a threshold of proximity, does the tail flick upward with surgical precision. The caiman flinches violently, thrashing backward, blood clouding the water. The ray vanishes in the ensuing chaos, leaving pain as both shield and smokescreen. Evolution has turned fear into function. Strike once, escape forever. Humans, however, are the accidental victims. Along riverbanks and flooded trails, fishermen and villagers often wade barefoot through shallow water, stirring silt where rays rest unseen. The result is an encounter as sudden as lightning. A foot lands, the sand erupts, and in that same heartbeat, the barb pierces tendon or vein. Accounts from the Amazon to the Orinoco repeat the same choreography. The victim screaming, collapsing into the water, clutching a foot that feels aflame. The agony is so distinct that indigenous guides can recognize it by sound alone. Traditional treatment calls for immersion in scalding water, a counterintuitive remedy that works because heat breaks down venom proteins faster than the body can absorb them. Yet even after first aid, the injury can linger, resistant to healing, haunted by phantom flashes of pain long after the wound closes. From a biological standpoint, the venom's purpose is elegant rather than sadistic. The molecules within it are not designed to kill outright, but to teach through suffering. They target pain receptors and vascular tissue, broadcasting a message to any would-be predator: never again. Like the bullet ant's sting or the caterpillar's spines, the stingray's weapon shapes behavior far beyond the moment of impact. Predators that survive one encounter often alter their hunting habits permanently, avoiding sandy shallows altogether. The ecosystem learns through pain, and balance is maintained by memory. What makes the stingray particularly remarkable is how its defensive anatomy coexists with sensitivity. Beneath that armored tail, its body is a network of fine electroreceptors, ampullae of Lorenzini, that detect the faintest bioelectric signals of nearby creatures. The same electricity that powers muscle and heartbeat in its prey becomes a homing beacon. The ray's feeding strategy mirrors its defense: patience, precision, and a single explosive act. A small fish passes overhead. The ray flicks upward, engulfing it in a cloud of silt, then settles again as if nothing happened. Its violence is not constant. It is conditional, governed by contact. In ecological terms, stingrays occupy a critical niche. By foraging through sediment for worms, crustaceans, and decaying matter, they till the riverbed, keeping nutrient cycles in motion. Their hiding places become safe zones for smaller species that cluster in the wake of their feeding plumes. Yet every creature that shares these shallows does so with caution. Even the cautious must cross where pain sleeps. River dolphins tread lightly with echolocation, skirting the edges of ray-dense sandbars. Capybaras entering the water often hesitate, their whiskers trembling above the surface, reading for vibration before stepping forward. Every movement at the edge of the Amazon is an act of calculation, because one misplaced footstep can change everything. Researchers studying freshwater stingrays have found that despite their reputation, these animals are remarkably tolerant of disturbance. Many stings occur only when they are cornered or stepped on directly. Their venom, costly to produce, is used sparingly. Each strike depletes reserves that take time and metabolic energy to replenish. For the stingray, avoidance is preferable to confrontation. It relies on camouflage, the oldest defense of all, reserving its weapon for those who do not listen to the warning silence. Culturally, the stingray occupies a strange dual role in the Amazonian imagination. It is feared, but also respected, a reminder of the river's unseen dangers and its unseen intelligence. Fishermen tell stories of the river's breath, the thin layer of silt that conceals spirits waiting beneath. In those tales, the stingray becomes more than a fish. It is the embodiment of consequence. It punishes haste, ignorance, and intrusion, forcing those who share its waters to move with mindfulness. From an evolutionary perspective, the stingray's story is one of irony. A creature shaped for concealment became famous through the very pain it sought to avoid causing. Yet in a system as competitive as the Amazon, deterrence is as valuable as offense. Pain, deployed with precision, saves lives, especially the stingray's own. The jungle above may be loud and restless, filled with territorial calls and hunting cries, but down here, silence is the currency of survival. The stingray has mastered it, waiting beneath the sand, breathing invisibly in a world that almost never notices it until it's too late. As dusk falls, the river turns from amber to black glass. The camera drifts close once more, low to the bottom, where the sand glows faintly under refracted starlight. A shape moves, then settles, disappearing again. The water is shallow, inviting, deceptively calm. A single ripple expands outward where a heron steps. Nothing happens this time. But beneath that sand, The stingray lies ready, spine sheathed but primed, the patient sentinel of the shallows. In the end, it is not the hunters of the Amazon that leave the deepest mark. It is the ambushers, the unseen defenders. Here, survival doesn't always roar. Sometimes it whispers through pain. The stingray is that whisper made flesh, invisible, motionless, unprovoked, yet capable of rewriting behavior across species with a single flick of its tail. As the camera pulls back, the river's surface smooths again, reflections unbroken, the illusion restored. Somewhere below, the sand shifts, then stills. The message lingers in the quiet current, a lesson older than fear itself. In the Amazon, the worst pain often waits exactly where you never thought to look.